Let's now move on to use our approximate method of analysis with our inflection points and how they relate to frames. This will work for gravity loads, that is, loads that are vertical in the same direction as gravity. In this case, there is a frame, a two-dimensional frame. It is 6 meters high, 12 meters long. It is fixed at A and C, and there is a corner there at B. If we remember our discussion related to what the purpose of this corner was, is that it stiffens the structure. I'll link at the bottom of this video in the description a quick demonstration to illustrate to you how a corner, introducing a corner, will stiffen up a structure. Okay, so let's get started. First things first, we have to figure out what the free body diagram looks like for this, because the ultimate goal is to draw the shear and bending moment diagram for this structure. The distributed load up here is 12 kilonewtons per meter. So I'll simply illustrate the reaction forces directly on this sketch. It's simply easier. Both ends are fixed. That means we have shear, axial, and moment at all locations. So an X and a Y force and a moment reaction at all locations. So I'll just show them right here. AY. AX. And a moment. I'm guessing at the directions. It doesn't matter. Our analysis will tell us whether our guesses are correct or not. Here we have CX, CY, and a C moment. Okay, a moment at C. Again, the directions are completely guessed. I don't know what they are, but my analysis will tell me. At this point then, we're ready to move on to our statics analysis, that is using our equations of equilibrium to see if we can get anything out of this. So, equations of equilibrium, I choose to start with sum of the forces equals to 0, where this direction is positive. In the x direction, I have AX, CX, and together they must add up to 0. Okay? Another way to say this is AX equals to minus CX. I really can't do anything else with this, so I'm going to park that equation, call it equation number 1, and move on. Sum of the forces in the y direction equals to 0. And what I get is AY, CY must equal this distributed load, which means that I have to figure out the equivalent point load that represents that distributed load. That distributed load is still there. It just makes it easier for reaction purposes to come up with an equivalent point load. It's easier on the calculations. Okay. That distributed load can be replaced with an equivalent point load right in the middle because it's distributed, uniformly distributed. I'm just going to do the calculation right here. It is 12 kilonewtons per meter times 12 meters equals to 144 kilonewtons. And it's located right in the middle at a distance of 6 meters from both B and C. So we get AY minus 144 plus CY. All of this equals to 0. So if we make this look a little nicer, we get the AY plus CY is equal to 144 kilonewtons. Again, not much else that I can do with this equation, especially given that none of these unknowns are matched in equation 1. I take it, I park it, and I call it equation 2, maybe to be used later. Lastly, sum of the moments. Sum of the moments at any location must equal 0, with counterclockwise equals to positive. I choose, simply because I can, to do my sum of the moments about A. I can do it literally anywhere else. Okay? I'm just going to choose one of the two. The supports usually are good, but I'm just going to choose A. So I'm going to do bottom to top, left to right, all of my moments caused by all of the forces. With respect to A, AX and AY do nothing, right? The distance is 0. I have to include the moment at A because it's a moment already, okay? It doesn't disappear because this moment is already a moment. It doesn't get multiplied by a distance. So we have the moment at A, and I'm guessing it's counterclockwise, which matches my positive. So that's why it's positive. Then I move the moment caused by this distributed load. It's going to be that equivalent point, 144, times a distance of 6 meters. This moment, with respect to A, is negative. It goes in the opposite direction of that. Okay, whatever we decided to pick as positive. Then the moment caused by CY is going to be CY times a distance of 12 meters. And this moment, with respect to A, is positive. Based on our positive convention, the moment caused by CX. CX times a distance of 6 meters. And this moment caused by CX with respect to A is negative. It's in the opposite direction. This. And lastly, the moment at C. We don't look at the moment caused by the moment at C. It's a moment already. Okay? So what do? We have to figure out if this is positive or negative. I guessed it going in that direction, which is the opposite of this. So negative. And all of this equals to 0. Okay? So look at this. 4 unknowns appeared in here. And only 2 of them appear in other equations. So this is not going to help us. We have to take this equation and park it somewhere. Okay? So I'm going to make it look a little bit nicer, and then I'm going to call it equation 3. Okay, so I just rearranged it a little bit to make it look a little bit nicer as follows. I'm going to call that equation 3. And here we are, 3 equations, 6 unknowns. So we have a problem. We really can't solve this because we're missing at least 3 more equations. So that is where inflection points are going to come in handy, because they'll allow us to maybe come up with at least, I don't know, 3 more equations. So first things we're going to do is we're going to figure out the deflected shapes. That is, identify where the inflection points are. We'll do it for this shape. So I've sketched over here as the next step what the original shape looks like, and then on top of that I'll superimpose what it's going to look like with this load applied to it. So first things first, it's a reminder that the corner will not move. It behaves like an intermediate support, so it doesn't move, okay? And by that I mean that the corner itself does not move, but I'll show you. It can rotate, it just can't move left or right, up or down. So first things first, this force is more or less going to cause this span to want to try to smile. Okay, grossly speaking. Make sense? Now the problem is, it's a fixed support there, so this smile has to frown to come back and straight, right? And this smile must end up at that corner. So what this means is this kind of comes down. But if this corner comes down like this, right? Then that means that this part of the column comes out because that corner must remain at 90 degrees. So let me show that more obviously, okay? If this area has to smile, then it must frown in order to come back up and be straight at the end, because it's a fixed connection, right? It can't rotate. So we have mostly a smile, then a frown, and then it's straight. When it reaches that corner, this corner is at 90 degrees. It stays at 90 degrees. So if we pushed it down here, that corner rotates, which means that this part of the column comes out, right? It bows out this way. But it just doesn't look like a bow. It too come back straight here because it's a fixed connection, right? They cannot rotate. So this one smiles again, but then it must frown in order to come back straight here, right? So it smiles, then it must frown, and then it's straight back to that support, okay? Now the nice thing about this is that already, if you remember the assumptions that we made about inflection points, our rules of thumb, which I'm going to link to you as a video below, okay, summarizing the 3 types of inflection points that we're going to use for this, link below. We're going to get the following obvious ones. 1, there's going to be one somewhere here at a distance from the fixed support, right? Remember that? Okay, so this is going to be an inflection point here and an inflection point there. Okay, they're at a specific distance from a fixed support. Then, because this corner, the corner in the frames, acts as an intermediate support, there was also an inflection point related to that. And it was at a distance from that intermediate support. Remember that? Now, the thing is, it must be on one side or the other, or both. It's on the side that has the load. In our case, this side, not this side, has the load. This side has the load. That means that inflection point is somewhere here. Okay? And this too, for an intermediate support, had a value. So I'm going to identify these inflection points. I'm going to call this inflection point 1. I'm going to call this inflection point 2. I'm going to call this inflection point 3. Okay? And then, a reminder that the distance from a fixed support, it was 3L over 13, 3L over 13. And for this one, I'm going to show it over here, L over 8. And remember, these values of L correspond to that portion of the structure. So this L and this L are 12 meters. This L is 6 meters. So let's figure out what that is, okay? L over 8 is 12 meters divided by 8. 1.5 meters. 3L over 13 is 3 times 12 divided by 13. 2.769 to 3 decimals. And this here, 3L over 13, uses 6 meters, okay, because that's the L for it. So 3 times 6 divided by 13. 1.385. Okay? So now that we have 3 inflection points, we have 3 more locations where we can cut this structure and get at least 3 more equations of equilibrium to help us solve this. Okay? So we're going to take a break here, and then I'll link part 2 of this video beneath, okay, in the description.